So I'm going to talk about some old and new things in combination. A lot of the latest stuff is work very much in progress. So I apologize if things I'm completing here. But I'm only going to give you a sketch of the idea. There's some complicated analysis in this. I'm only going to sketch the details. I think the ideas, though, are actually very easy to understand. Okay, so I said it was a mixture of old and new. So let's start with something slightly older. So here's something which you all know. Here's the problem for steady water waves. So here's my coordinate system. So X, Y, and Z. So Y is always vertical for me. So X and Z will be the horizontal coordinates. And what you see here are the Euler, the governing equations for steady water waves in a frame moving with the wave. Okay, so the point here is the velocity, you can see it here, is a vector c. So I'm not assuming the waves are moving in any particular direction. They could be moving in the X direction, the Z direction, or in some other direction, in some direction of your choice. And those are the equations which you need to solve. So U is the velocity here, depends upon X, Y, and Z. Now, I've non-dimensionalized everything. So you see the depth here is 1. And this beta then is the Bond number, so the dimensionless coefficient of surface tension. And this is the reason why the gravity is equal to 1, is because everything's already non-dimensionalized. This is to make the whole presentation a bit simpler to understand. So you might wonder why I wrote it down in terms of the velocity field U and not immediately in terms of a scalar potential. We'll come to that in a second. Just a few more bits of notation. So these are the conditions at the boundaries. N is obviously the normal vector at the surface, and this J is the normal vector at the bottom. So the I, J, K are the three usual unit vectors. And so what you have to do is solve these. And once you've solved these, you see you recover the pressure from this formula, minus 1/2 the gradient of U squared minus Y, and then you find that U and P satisfy the steady Euler equation, and so you've solved your problem. The notation here, by the way, if div and curl are written out in full, it's 3D div and curl, but you see you've got nabla, this means 2D, just X and Z. This should be clear from what's coming later. So I've been interested for a long time in so-called fully localized solitary waves, and this is sort of this isn't even an artist's impression of them, but we'll come to that in a moment. So those are solitary waves which move in one direction with a fixed speed, and they decay to 0 in all directions, so in both horizontal directions. And that's a problem I've been interested in for a long time. And now we come to my connection with Jean-Marc. Let me just show you maybe pictures of what they look like. So these are actually the two types of fully localized solitary waves that you get. The scales here have obviously been exaggerated. Yeah, so in fact, the waves we get are small amplitude and long waves. So they've been rescaled so you can see the essential features. There are two types. Let's call them KP and DS type for reasons which will become clear. So about 20 years ago, maybe more like 25 years ago, I can't remember exactly, I met Mark Cooker at a conference and we started talking about this stuff. And I said, I think I can prove rigorously the existence of such waves for the full water wave problem. And he said, that's great. Well, why don't you come to East Anglia? Because we've got this stunningly good new professor there, it's Jean-Marc van den Broek, who just arrived from Madison. And he might be able to compute them numerically. So that's what happened. I visited them and gave a talk on, at that point, a sketch of my theory. And indeed, they then got a postdoc to help them work on computing these waves. And that postdoc was Emilian, who's sitting at the back. And the rest is history, as they say. Since that time, there've been a lot of very, very nice numerical computations of these waves. And in that time as well, I've refined the existence proofs which I had at the time. And so everything fits together really well. So this is a really good example of synergy between analysis and numerics. We always claim that it exists, but in this particular case, it really does. Okay, so I want to talk about like a new development in this now, because we're talking about waves in the next 20 years, not in the past 20. And so I'd like to now go from 3D irrotational waves to 3D waves with vorticity. So let's go back to the equations which I had. So now this is exactly the same system as before, but now you see I have changed the assumption that the waves are irrotational to this, that the vorticity should be proportional to the velocity. This type of flow is called a Beltrami flow. It comes up in a lot of different contexts, also in plasma physics, lots of different situations. And the point here is that if you change the equation like this, you can still do as before. If you can solve this equation, it's still the case that you can recover the pressure in this way, and it gives you a solution to the steady Euler equation. But now we're talking about 3D waves with non-zero vorticity, and you can see from the way I've done it, these waves will always have non-zero vorticity. So this is the new problem. I'd like to find fully localized solitary waves to this problem, and let's call them Beltrami solitary waves, or Beltrami water waves, I've called them. Wasn't quite sure what name to give them, so I've called them Beltrami water waves here. Okay, so first of all, I'm going to give you a sketch of the theory of how to do this, and there's a couple of surprises in here. A lot of it is similar to water waves, but similar in a way which you might not expect. Okay, so first of all, these are the equations in the frame moving with the wave. So basically what's going to happen is these solitary waves are kind of riding a trivial solution, a laminar flow. So let's have a look what the laminar flow looks like. So for steady water waves, the laminar flow is just, everything moving uniformly, uniform flow. And your solitary waves ride that flow. That's what happens. For Beltrami waves, it's a bit different. This is how the trivial solution looks. Again, laminar flow, the free surface is flat. But the trivial solution looks like this. So C1 and C3, as I really apologize for my notation here. It drives my co-authors mad. You see, I've got X, Y, and Z, but Y is vertical. So the horizontal coordinates have to be, they have to be C1, C2, C3. So the velocity has to be C1, C3 instead of C1, C2. Yeah, I mean, Eric claims I do this especially to infuriate my co-authors, but that's how it's going to be. So these are the two components of the wave speed, C1 and C3. If it upsets you, think 2 in your head. Okay? But you can see that you've got a kind of flow which is swirling. What's happening is this is the flow in the frame moving with the wave. You've got the flow which is swirling, and the solitary waves are on top of this flow. This is a special kind of one of the ABC flows. But I can't remember, just two of the A, B, and C are actually 0 in this flow. But I can't remember if it's an A, B, or C flow. But it's actually a special case of those. So you can see it's a completely different sort of setup in the fluid. Okay, so very good. And again, what I'm going to do then is to write my flow as a perturbation of the trivial flow, as always. So V will be the displacement relative to these, and V will be small then. Okay, so let's go back to steady water waves and review what we know. Now, this I think is known to everybody. What do we usually do? We've had this several times this week. So let me just go through it. You might think, well, why is he going through this old stuff? It's because I'm going to modify it in a moment to get the new stuff. Yeah, so this is what you'd usually do, right? If you're doing steady water waves, you write your velocity as the gradient of scalar potential. And then you find that the scalar potential is harmonic, Neumann boundary condition at the bottom. And this means that these three parts of the equations, which we saw, are automatically satisfied. You're always incompressible, you're always irrotational, you always satisfy the condition at the bottom. And so then the problem is what happens at the top. And in fact, you can recover the boundary conditions of the free surface from a famous variational principle, going back to, say, I think Luke was probably the first, but Sakharov as well around the same time. And here's the variational principle. Let's have a look at it. So you have two variables, eta and psi. And psi is the evaluation of the velocity potential at the free surface. And so here's the formula for the variational principle, written in the way Luke would have written it, rather than the way that Sakharov would have written it. But we haven't forgotten Sakharov. We're going to come to him in a moment. So here's how the variational principle looks. You've got the potential in here, but the potential is given by solving the boundary value problem with Dirichlet data at the surface. So this is one version of the variational principle. Kind of the simplest one. Again, I mean, I don't have to show you that that's the case. You'll know that that's the case. Okay, very good. So then once you've realized that, the next step really in this story is the Sakharov-Craig-Sulem formulation. So what they did was to introduce a Dirichlet-Neumann operator. So this is sort of the Craig-Sulem part of the story. Sakharov already had the variational principle, and it was Craig and Sulem who said, let's use a Dirichlet-Neumann operator. And again, you all know how this works. Dirichlet-Neumann operator works by solving the problem for a harmonic function phi with the Neumann condition at the bottom and Dirichlet data at the top on the free surface. And it gives you, it basically, you feed it with the Dirichlet data and it spits out the Neumann data. So here, this capital N is the non-normalized normal vector at the surface. It's convenient to use it not normalized here because then it works in the formula for the variational principle better. That's the only reason. And you can then rewrite the variational function into functional in terms of the Dirichlet-Neumann operator. There's no trick here. This is the same formula as before. Instead of having the integral over the bulk, I've now got the Dirichlet-Neumann operator. And when you write down the Euler-Lagrange equations, those are essentially the dynamic and kinematic conditions at the free surface in water waves. Okay, so I mean, it's kind of a tutorial right up to now. And this is what you give. This is what you say to undergraduates or graduates when you first discuss this. Again, notice everything in steady frame. Yeah, and again, maybe the slight thing which might slightly irritate you is that the C is again, I haven't chosen the direction for the velocity yet. Okay, there's a reason for this as well. So here's maybe a slight thing which maybe is not so well known. You can actually write this as a single equation if you're looking for steady waves. Just do it formally. I mean, we're just getting the idea now. You see, the first equation you could solve for psi as a function of eta. Right? I mean, psi is minus the inverse of g operating on C scalar product with the gradient of eta. And then you could plug this into the second equation, and this will give you a single equation for eta. I mean, that's key. You can do that. So there it is. This is exactly that. The only thing I've changed here is instead of writing in the notation I've used before, I've simply introduced a new L of eta and C, which is given by this. So this is a single equation for water waves. Now, as Vera said in her talk, there's no approximation here. This is the water wave problem. Yeah, I mean, maybe it's more spectacular in Vera's talk because you looked like you had a simple, Hilbert transform. This is kind of the 3D version of this, but it's brutal. It still involves a non-local operator, in this case L, which is sort of the inverse of G. Okay, so this is kind of a single equation for that. Okay, so I wrote down this equation the first time about 10 years ago. I was very proud of it. And then I gave a talk on this last year, and then it turned out that Katie, in fact, had written down this equation before me. So this is now to be called the Oliveras equation. For the purposes of this talk, at least, just to show that we're all friends here. Okay, so the point here is you can reduce everything to a single equation for eta. Just a few comments about this equation. All right. You might think that you have to work out the inverse of the Dirichlet-Neumann operator, which is a pain. In fact, you don't, because if you just think the inverse of a Dirichlet-Neumann operator has to be a Neumann-Dirichlet operator. So if you just look at the boundary value problem, which is defining G, and what the corresponding one defining the inverse is, you find that you can define this L directly in terms of a boundary value problem. To work out L, you solve this boundary value problem. So you feed it with an eta. This is a Neumann condition at the surface. You solve it for phi, and then you take the gradient of phi. And this will give you the L, which I'm talking about here. L is vector valued. Okay, but the point here is simply that you don't have to work via the inverse of G. You can actually work directly with the boundary value problem. This actually saves you some headaches when you come to do this. And so another fact about this is a theorem which I'm not going to prove. The operator L is an analytic function of eta and C in suitable function spaces, which shall remain under the carpet for this talk. Yeah. And I could give, I've got a couple of methods for doing this, one in particular, which I think is very, very nice and very easy to understand. Essentially, what you have to do is you take the boundary value problem in this variable domain, you map it to a fixed domain, and then you simply have to do a perturbation argument, look at the linear part, and you show that you can invert the operator appearing there, essentially by using a Fourier transform and a Green's function, and then you use the analytic implicit function theorem. So like Miles was saying in his talk, the implicit function theorem is one of the most underrated tools in analysis because you can do so much with it. So the proof of this is actually very simple and very beautiful, but I don't want to get into that. And again, this just means I can expand everything in a series of eta and c, and I know that the series converges. That's all it means. Okay. And again, this has a variational structure. The two equations we saw on the page before, which involves xi and eta, came from a variational principle, and I just solved one as a function of the other. So if I insert xi as a function of eta into the original variational principle, I get a new variational principle just for this. This has a variational structure. You can always do this when you're working with a variational principle. Okay, so review. That was just a review, right? Maybe the slightly new thing is you have the single equation for eta. So let's now go back and change the context and look at our Beltrami wave. So now the curl isn't zero. Now it's a constant times u. This, by the way, is supposed to be an alpha. These fonts are very fancy, but they're kind of useless because you can't tell what the letters are. So this is an alpha u. Okay, and again, we write everything as a perturbation of this fancy trivial state. Okay, now, all right. Now, how would you proceed with that? Well, I mean, you can't write v as the gradient of a scalar function anymore. But you could write it as the curl of a vector stream function. All right, and so the stream function would have to satisfy these equations. Curl of A is alpha curl A, divergence of A is 0, and use the boundary condition at the bottom. Now, if you do that, you will again satisfy the three equations that we had before, that it's irrotational, incompressible, and you've got the Neumann condition at the bottom. Okay, so now you might ask the question.
What's the connection between V and A?
So V is the curl of A.
Ah, okay.
Yeah, so instead of writing V as gradient of phi, now V is curl of A. You might think, now, what's the point of this? Because I mean, it seems to be making the equation more rather than less complicated. But bear with me, because I mean, there's some kind of miracle about to happen. All right. So you might say now, okay.
Why is the curl of V 0?
Because no, it shouldn't be. It should be the curl of V is alpha V.
Yeah.
Sorry.
Okay.
Yeah. I thought I did so well getting rid of the typos yesterday. Yeah, I'm sorry.
No.
There's always somebody who checks the side.
Be the curl if he's not 0.
The curl of V is alpha times V. That's what I want, right?
That's right.
That's what I said, and that's what I want. Thank you, Paul. Yeah. Okay, so wouldn't it be great if I could reformulate everything in terms of a single equation for eta like I did before? I say it would be great, but it seems to be impossible. Let's show you some. Let's just have a look at something. So let's take a vector f with 3 components, right? And now let's form this vector f parallel. Works like this. So you evaluate it at the free surface, and then you do this little operation to it. It turns a vector with 3 components into a vector with 2. All right, here's the formula. If you want the explanation, it's this. So you take the tangential part of f at the free surface, and then the horizontal component of that. So this is the horizontal component, the horizontal part of the tangential part of f at the free surface. All right. If you like physics, you like that. If not, you like the formula. All right. Now, take that, and this is just a vector with 2 components. So you can write it using the Helmholtz decomposition into a part which is the gradient of something, and the part which is the perpendicular gradient of something. If you want the exact formulae for them, here they are. Yeah, but the point is you can write any vector with 2 components like this, the gradient of something plus the perpendicular gradient of something. So in particular, you can do it for this f parallel. So again, it's the horizontal part of the tangential component of the f at the surface, and then you decompose this into its 2 parts in the Helmholtz. Now, and here's a stunning result. I thought it was stunning. There's actually a variational principle for the Beltrami problem in terms of eta, and the thing that plays the role of the evaluation of the velocity potential in the Sakharov-Craig-Sulim formulation is actually you take the velocity v, which we had up here, the one which satisfies curl V is alpha V. You take that, you work out F parallel and take the gradient part of that. And that plays the role of psi. And then, in fact, you find a formulation of this problem in terms of eta and psi, which is completely analogous to the Craig-Sakharov-Sulem formulation. Okay, let me just show you how it works. The details in this are kind of lengthy, but not really so difficult. But let me just show you how it works. So the boundary conditions at the free surface follow from the variation principle like before. Here's the variational functional. So this part should remind you, this part gives you the, the velocity and the bulk. Then you've got a part here, which is obviously giving you the, the curl U is equal to alpha U. This part is giving you that. And then you've got some terms which are giving you the conditions at the free surface. Again, I mean, don't obsess over the formula. I'm just going to give you the flavor here. But I should tell you what the ingredients are. The A star, which you're turning out here, this is the vector potential, which is giving you the trivial flow. And then this gamma of eta is kind of a term which makes sure that all the other terms balance out, basically. Okay. And so my comment is that the working in terms with the vector potential A, this is a variational principle for the equations which you saw. And if you do exactly the same thing that you would have done with the loop principle, you will get the Beltrami equations. Okay, don't do the calculation because it would take me a couple of pages, but it isn't difficult, just slightly lengthy. Okay. Again, yeah, A we had before. This is the potential that we had here. Now, to complete the problem, I have to tell you what the conditions are at the free surface. And this is the condition at the free surface. So you have, as in the Craig-Sulem-Sakharov formulation, you had to solve something which is related to the Dirichlet-Neumann operator, and the phi was equal to its trace at the free surface. Now, what you have is that the parallel part of the curl of the free surface is the gradient of psi minus something else. And the point here is, you see, this is the gradient part of that at the free surface. Okay, so this looks like a hefty variational principle, right? But it's kind of super neat and has exactly the same flavor as the one we saw as the Sakharov-Craig-Sulem formulation. Okay, so we have succeeded in finding a variational principle which is completely analogous to theirs, but looks like it's more complicated. In fact, it isn't. It just looks like that in theory. Okay, and I mean, it could be, I could set it as an exercise to verify that what I'm saying here is true. It really is true. You might ask, by the way, how I thought of this. The answer is, I spent a lot. I mean, it took me 2 years to think of this principle, but I had two pieces of help. Brooke Benjamin, who was my supervisor, he had an alternative variational principle for water waves in which you don't use eta and phi, but you use eta and the traces of the velocities of the surface. And when you look at that closely, you see this parallel sort of coming up there. So I had this idea that the parallel must be important. And there's a paper by Lan and Castro about 5-6 years ago in which they do arbitrary distributions of vorticity, and they use this as well. So I had an idea this might be important. Okay, so let's just follow this path for a moment. All right, you might say, well, okay, this is a mess. Wouldn't it be good if there was like something which is a bit like the Dirichlet-Neumann operator? And there is. So there's a generalized Dirichlet-Neumann operator which works like this. You solve this. You start with eta and psi. You solve that boundary value problem. I just say that boundary value problem to emphasize the fact that I don't really want to take you through it. Yeah. But you see, the main difficulty here is that you got the strange boundary condition at the free surface. So the curl of A parallel at the free surface, there's the gradient part, there's the part which is the anti-gradient part, and this psi is appearing there. You solve that, and then you evaluate the curl at the free surface dot product with n, just like in the Dirichlet-Neumann operator, except now it's not the gradient of phi, it's the curl of A. But it's just the same sort of structure. And amazingly, you can rewrite the variational functional in terms of the generalized Dirichlet-Neumann operator. Here it is, H. And you can write down the Euler equations for those. Again, two equations, just like before. And just like before. you could now invert the first equation to find psi as a function of this stuff. Now n involves eta, so you have an eta in here, and you put that into the second equation, and you will get one equation for eta. All right, which we shall now show you in all its glory. Here it is. Here's the single equation for eta. U star is the trivial flow, and U star H is the horizontal part of it. So what should we call this? Let's call this the generalized Oliveras equation. So sorry to embarrass you, Katie. We are all friends here. Okay. So the point here is everything you could do for the single, for the Craig-Sulim-Sakharov formulation as a single equation, you can now do for this. And in fact, it all works out very well. The non-local operator occurring here, which involves obviously the inverse of the generalized Dirichlet-Norman operator, can also be defined directly in terms of a boundary value problem. And in fact, if you play with it a lot, it turns out that you can write it as a simpler equation only involving the Laplacian, but you have to do this is equivalent to the original boundary value problem. This isn't easy to see why that is. I'm just trying to give you the flavor of what you can do here. And the point is the analogy with the previous one. Okay, so you can again define this directly, and you can show that the operator you've got here, just like before, is an analytic function of eta and c. So you've got a complete analog here. And the point here, and again, you have a variational principle for the single equation, everything like before. So the message to take from this is, it looks like it's a super complicated variational principle. In some ways it is. However, the end result is a single equation for eta, which is no more complicated than the equation that you had for the Sakharov-Craig-Sulim formulation. Yeah, everything that you had there has a complete analog here. Okay, so having formulated everything as a single equation, now I'd like to show you what to do with that equation. Now, the next part of my talk basically could be the same for irrotational waves, because the analogy is now given. The proof, by the way, of the analyticity of this is also super nice. This is a vector valued thing. So if you do the same proof as before, you find yourself not working with a Green's function, but with a Green's matrix, because you've got coupled ODEs. This theory probably exists somewhere, but just like Miles' version of the implicit function theorem this morning, I couldn't find it. So I had to reproduce this theory from scratch, which was a real pain, but worth it in the end. Okay, so let's take a look. So now, the first thing you do when you're looking at equations like this is to look at the dispersion relation. So those are solutions of this form, exponentials. Again, K1, K3 for the, because it's X and Z, I'm sorry. Yeah, what you find is this. So the dispersion relation looks like this. It's written down fully. K and K perpendicular, those are from the K up here. And this function f basically has a hyperbolic cotangent or a cotangent, depending on whether you're smaller or larger than alpha. This is just a calculation. Again, what's the running joke is give it to a graduate student and see if they can do it. They should be able to do this. If they can't, you should get a different graduate student. Yeah. And what to do with the variational principle, with the dispersion relation? You can write it, in fact, in terms of sort of polar coordinates. If you write it in terms of the magnitude of k and the angle between c and k, you get a form like this, which is slightly more amenable. And so what I did was I said, okay, let's take this thing as a function of theta, and let's look at the value of theta, which minimizes the wave speed. To minimize the right-hand side, this is just a simple equation. There's a certain angle, let's call it theta min, which minimizes the right-hand side. And then when you plug that value in, you get a minimum value of the right-hand side. And so always fixing on this angle between K and C, which minimizes the right-hand side of this, you eventually end up with a dispersion relation for C in terms of the magnitude of K. And the reason you do this is because now you're on comfortable territory now, right? You now got C as a function of K. Yeah, but remember that there is an angle here as well, which you've chosen to minimize the right-hand side of this relation which came up. So there is this angle. In other words, the waves are going to choose the angle in which they're traveling in, the direction in which they're traveling in. Okay. So what does the dispersion relation look like? Oh, kind of groovy, huh? So you can get various cases. What turns out there are two values of the dimensionless surface tension, so bond number, if you like. Let's call them beta 1 and beta 2. Beta 1 is always bigger than or equal to beta 2. And depending on the various values, you get 4 possibilities. It looks like there's only 3, but this is because of the various, the various cases here. There are two betas which depend on alpha. Beta 2 is always bigger than or equal to beta 1. So these 3 cases are where beta 2 could lie, in relation to beta. If beta is less than beta 1, you always get this global minimum. If beta is bigger than beta 1 and beta 2, which happen to be the same, you always get that. Global minimum is at the origin. You get the same picture if beta is bigger than beta 2, which is bigger than beta 1. And if beta 2 happens to be bigger than beta 1, you get this interesting case, which I hadn't seen before. Unfortunately, I don't have much to say about this today. We're now getting into the work in progress territory. But what I do not know is, you see, you've got a minimum here and a minimum here. Now, if that minimum is higher than that minimum, you're essentially, in this case, for local bifurcation theory. If that minimum is less than that minimum, you're essentially, in that case, for local bifurcation theory. I do not know if they can happen to be the same. If they would, that would be really cool, because that's a new type of wave, and I don't know how to handle it at the moment. I don't know whether they can be the same. I mean, what you have to understand here is that beta 1 and beta 2 are complicated functions of alpha. I said that in my dramatic voice. Yeah, so it's very difficult to do anything explicitly with them, even to prove that you have this form is actually quite difficult. Okay, so what I want to do is just to focus on these 2 cases and show you what I would do, and what's about to come could be the same for irrotational waves as well. Now, so I apologize if you heard me talk about that before. From this point on, it's basically the same as for irrotational waves, but remember, you're working with more complicated variational functions and so on. Okay, so here's the first case. Now, if you're doing modeling, what would you do here? You would say, okay, the local bifurcation should be near here. And if I'm just doing it formally, I should make this ansatz, the KP ansatz. So scale eta like this. So X is scaled by epsilon, Z by epsilon squared. The amplitude here is epsilon squared, expand in a series. And epsilon is found, you take the minimum here and you go a little bit below the minimum. That's where the epsilon comes from. But remember, you've actually got 2 directions of the wave speed now. That was kind of hidden a little in the previous thing, but you've got these 2 directions. So you have to, you have to scale the speed like this. You have to take into account, you've got this direction theta min, which we had before. Okay, but now plug this in, expand everything in powers of epsilon squared. Now remember, what you're using is a single equation for eta, which has h, which is an analytic function, or n, which is an analytic function. So you have to expand that analytic function. Yeah, so it's a pain, but it can be done. And at the end of the day, it turns out it's not so bad. You do indeed get the KP equation. And for your pleasure, I have written down the coefficients explicitly. Here they are. So they're really not so bad. I mean, so it's actually, you can live with these. This calculation only takes kind of, well, 6 weeks the first time, and then when you do it correctly, another 3. These D's are Fourier multiplier operators. So they're not coefficients. Again, it's D3 and D1, of course, K3, K1. So D1 is IK1 and D3 is IK3. So to calculate this, you take the Fourier transform of zeta, multiply it by that operator, and take the inverse Fourier transform. Okay, so you get the KP equation. And what do we know about the KP equation? Here it is. Here I've put all the coefficients equal to 1, because I think you don't want to see the C's anymore. Yeah? And you can actually scale it to do that as well. But it has an explicit solid wave solution, which looks like this. No guarantee I've got the coefficients correct here. I think it's -12. Okay. And that is actually, you can characterize it as a critical point of a functional. Now you might say, why? I've got an explicit formula. Why would I want to use this? But the point is, if you wanted to, you could prove the existence of a critical point of this functional, and it would be that, of course. I don't know that it's unique, but let's just say it is for the sake of argument. But the method that you'd use is actually robust under small perturbations, which means if I add a little perturbation here, then I would be able to use the same method to get a wave which is a little perturbation of that one. That's the important thing. I'll come to that at the very end. You speed up a bit because I'm running out of time. For this case, you do exactly the same thing. If you're a good modeler, you know what to do here. Davies-Stewardson modulation ansatz. Again, the C's are perturbed in the same way, just below the minimum. This time you use a modulational ansatz. This calculation takes a year. What you get is an equation of Davies-Stewardson type. Let me put it this way. So you probably haven't seen the Davies-Stewardson written like this before, but it is just an equation of Davies-Stewardson. So this A is a matrix. This L is a Fourier multiplier operator. It's a linear combination of these three with coefficients which depend on, in a hideous way, upon alpha and beta. I mean, I really want to underline hideous in blood here. Yeah? So I've done the calculation once. I have to do it again at least one more time to make sure that that it's plausible. And the point about the Davies-Stewardson equation of this type. So let's look at it again. So there are values of the alpha and the beta, the parameters in the problem, for which A and LD are positive definite, and this coefficient C is positive. And then this is an equation, a Davies-Stewardson equation of, let me get it right, elliptic focusing type. I apologize to the DS specialist if I got that wrong. That's what I think it should be. What I mean is of the type that has a fully localized solitary wave solution, which looks like that. This is how the predicted free surface of the fluid would look. And again, you find this by variational methods. And this time there is no explicit formula. You have to find it by variational methods. Okay, now again, I could show you how to do that, but just believe me, you can do it by variational methods. And the variational method is robust under small perturbations again. Okay, so how far have we got? We've got to say, okay, we've now got a formulation of the Beltrami wave problem as a single equation for eta. And if we do formal modeling from the dispersion relation, we recover versions of our old friends, the KP and the DS, which predict the existence of fully localized waves. Okay, very quick feel of how to make this rigorous, because I'm an analyst, I mean, I like getting these things, but I can't sleep at night unless I can prove that it really exists, That's why I'm aging faster than everybody else. So what you do is you use variational methods. So the J is the variational functional for the single equation formulation of the Beltrami problem. And again, here's the version for KP. This is what we did to find KP. We used this ansatz. But if you look at what's happening here, what we're actually saying is we're looking for waves which in Fourier space are localized near wave number 0. All right. So what you do is you say, okay, I take my eta and I split it into two parts. One with support in Fourier space lies in a kind of bow tie region like this. And the rest, you take the Euler-Lagrange equation for your variational principle, split it into two parts correspondingly. This is like Lyapunov-Schmidt. And then you solve for eta2 as a function of eta1 and plug this back into the variational principle to give you a reduced variational principle. So it's very much like Lyapunov-Schmidt. You realize that the action is going on in a region like this. Your KP ansatz tells you that. You split the Euler-Lagrange equation for your variational function into two parts, solve for the kind of like the non-important part as a function of the important part, and plug back in, reduce. Same thing exactly if you're looking for Davies-Stewardson. Here's Davies-Stewardson. Again, this time the action is going on in two parts of Fourier space, which are with wave numbers near K1 is omega, K minus omega, and K2 is 0. And again, you split your Euler-Lagrange equation into two parts, one for eta2, one for eta1. Solve for eta1 as eta2 as a function of eta1, plug it back in, you have a reduced variational principle. This is a sort of Lyapunov-Schmidt method. Okay, this What's really interesting about this is basically you're redoing the steps you did before formally in a rigorous way, but it's basically the same calculation. Yeah. Okay. And finally then, at the very end, you take the eta1, which is the part where the action is, you actually apply the exact KP or DS scaling to it. And what you find is that then your reduced variational principle gives you exactly the KP variational principle plus small rest, or the DS variational principle plus small rest. And what did I say before? I said that the variational methods that you could use to find the existence of critical points are robust under small perturbations. Well, here are small perturbations. And so you can apply the methods that you used before, and you will find critical points of these. And what's beautiful about this is, I mean, it's really the same argument for KP and DS as it is for perturbed KP and DS. So you've really, I mean, you've achieved a lot here. You have not only proved the existence of fully localized Beltrami waves, but you've also justified the use of these model equations in finding those. So, you know, we've done pretty well here. Okay, this is all still work in progress. Work in progress means basically means I still have to make sure I've calculated L, A, and C properly. That's what work in progress means. The variation principle itself is published. It's a paper with my former PhD student Jens Hahn. And there are various other people working with me in various aspects of this. It's unclear who's going to be a co-author of what. That's why I haven't mentioned names explicitly. But some names I do want to mention here. People who've helped me is Erik Wallén, who's helped me here, and Doug Nielsen and Stefano Pasquali, who are postdocs of one or both of us at various times. They're helping me with this. Let me complete the circle now. How did this all start? This all started with me being able to prove the existence, or at that time thinking I can prove the existence of fully localized steady water waves, and going to Mark Cooker and Jean-Marc and say, wouldn't it be nice if somebody could compute these? All right. Wouldn't it be nice if somebody could compute numerically the Beltrami steady waves that I talked about today? Now, there are a lot of people in the audience who are experts on computing 3D water waves. I don't know, maybe I should focus a bit on the younger people who have the more energy, but I appeal to you. It's an exciting project which needs non-trivial modifications of the waves of the methods used for numerics for steady water waves. I wanted to say I'm in numerates. That's not kind of overstating it, right? But I can't do numerics at all. I've got no talent whatsoever with numerics, but there are a lot of people here who do have talent. And so if you think this is an interesting problem, please talk to me. I'd really love to cooperate with somebody who can compute these. If nobody talks to me, then I'm going to start approaching people myself later. So that's that. I hope that completed the loop well.